So our next speaker is Matthew Reimherr from Penn State. His talk is Manifold Data Analysis with applications to high-resolution 3D imaging.
Okay, thank you very much. And thank you to the organizers. So this has so far been fairly enjoyable, and I'm excited for the rest of the week. So before I get started, so let me just sort of acknowledge contributors to this work. So the first is my PhD student, Hyunbin Kang, who is actually graduating this year, so she'll go to Western Michigan as a faculty. And then the person who sort of really made a lot of this work possible is Mark Schreiber, who's in anthropology at Penn State. So if you haven't worked with anthropologists, I highly recommend that you do so, actually. So the anthropologists collect extremely good data, and it's usually extremely interesting data as well. So they love to scan things, they love to measure things, so and they like to tackle sort of really interesting problems, I think. And then the last one is Peter Klaas, who is electrical engineer and who's really worked with Mark a lot in terms of sort of building up the pipeline for a lot of this data that you're going to see. And then lastly, I'd like to thank sort of NSF and NIH for their support. Also, just as a little bit of advertising, so I'm not trying to take on Jim here, but we have sort of a new book on functional data analysis. So this is basically coming from Piotr Kokoschka and myself. So we've taught functional data analysis at our respective universities now several times. And so this is sort of the notes that came out of that. So it's really designed as more of a textbook, especially for sort of advanced undergraduates and master's students. So lots of R code, lots of problems and things like this in case. Yeah, so again, so teaching functional data courses has actually been pretty fun. So I've actually gotten quite a few people across the university, not just in statistics. And last time I taught it, I reached room capacity. So I had to start really, I couldn't even sign people in anymore, so this was against the fire code, so I had to really be selective. Okay, so the overview for this talk is fairly standard. So I'll go over some sort of motivation and goals. We'll talk a little bit about previous work, especially manifolds and functional data analysis, because these have been cropping up more and more. And then I'll spend quite a bit of time on our sort of framework and especially this application to 3D faces. And so the way this talk is timed, you can feel free to interrupt me whenever you like, because otherwise I'll cruise through and then we can just go get coffee. Okay, so the motivation for this work is coming from a study called ADAPT. And so like I said, Mark Schreiber has been collecting data on human faces now for quite a while. And so he's now up to over 6,000 faces. I don't know if he hit 7,000, but he's sort of continuously collecting this data. And so it just keeps growing each year. And so there's sort of a lot of processing that goes into these faces, but sort of after everything is said and done, you end up with over 7,000 points measured on each face. And so each point that you measure on the face is now a 3D coordinate, right? So where is the tip of your nose? It's a 3D coordinate, right? And so now you have 7,000 points across this face, all the faces, which sort of tell you how it's shaped and where they are. Now, in addition to these faces, because he's an anthropologist, he has a lot of other interesting variables that he measures. In particular, he has various demographic variables. And what's maybe really interesting is he's also genotyped a lot of the subjects. So he's up to 3,000, up to 3,000 subjects. Again, he's probably cruising even higher. And with each of these subjects, he has, a lot of them are genotyped at over 1 million SNPs. So this is a fairly high resolution genotyping. So that's a lot of genetic mutations to have at your disposal. So this is just a very large, interesting, rich data set. And a lot of anthropologists collect, maybe not data exactly like this, but a lot of sort of similar types of data. Okay, so what is his sort of general workflow? So this is, I have no contribution in this part whatsoever, but I think it's helpful at least to understand sort of how the data is collected and processed and things like this. So at the very beginning, so this is A, so the subject is asked to sit there in a fairly neutral expression. the subject is also not allowed to have facial hair. Okay, so I'm not allowed in the study, Richard's not allowed in the study, unless you're willing to shave your mustache, and then we can add you to the study. But I told them no, I wasn't going to shave my beard to get into the study. So no facial hair, you have to sit in a neutral expression, and then they basically scan sort of the whole upper region of your body. Once that's done, they then basically sort of try and cut away anything that sort of isn't related to the face and maybe sort of the neck region, so they don't want the shoulders and things in there. And then what they do is that, so this is B, and then they go to C, which is actually they take the reflection of the face. So anthropologists, they are interested in asymmetries, but at least Mark, he likes to analyze asymmetries separately. Okay, so what he wants to do is he wants to take sort of the original face, he wants to take the mirror image, and then he sort of wants to combine them at the end to get sort of a reflected symmetric face. Okay, so he will look at asymmetries, but sort of asymmetries, at least for him, is sort of viewed as sort of a type of noise that he sort of would like to get out at the beginning, and so I said, okay, that's fine, we can do that. All right, and so then the real sort of trick of this, and I think this is what Peter spent quite a bit of time on, is that for both of these faces, for B and for C, what you'd like to do is you'd like to fit a mask of landmarks over the top of the face. Okay, so this is where those 7,000 points come from. These are basically 7,000 landmarks. And so to do this, they'll basically put in actual landmarks, sort of like the tip of the nose, edges of the mouth, the eyes. So these are actual landmarks, and they'll use those landmarks and the faces to help guide the fitting of these 7,000 points over the top of the face. Okay, so I was going to sort of make connections to things like Silence of the Lambs, okay? But this is probably like inappropriate to put pictures up related to that movie, but it's the same sort of idea. So you're fitting this over the top of the face. And so you do this to both the sort of original face and the reflected face, and so now you have each of these faces represented as basically 7,000 points in 3 dimensions. You'll then basically combine them at the end to get this symmetrized face. And then at the very end, all the faces are sort of aligned, okay, and rescaled so that everything's sort of on the same scale. Okay, and so in the end you get these sort of nice 7,000 faces. They've sort of all been nicely processed and aligned, and they're all represented as these 7,000 points. Okay, good. Okay.
Just,
yeah, please.
If I took the same person and brought them in 2 different days and repeated the whole process, how well do these alignments and these 7,000 points agree? I mean, is it pretty stable?
They should be extremely stable, actually. So I think the only the only thing you could potentially worry about is if so the person is not oriented in exactly the same way. But that should be taken care of at the end when everything is sort of rotated and scaled and aligned. So in this sense, it should be okay. But you're right. I mean, the raw scans that you get, right, this could depend on sort of how they're positioned, how they're...
Yeah, I don't know what else...
Or if they're...
into the
right.
algorithm, if there's a little... how sensitive it is to small...
Yeah, so in theory it should actually be quite robust.
So with the, you said they're symmetrized.
Yes.
The original and the reflection, and then are they just averaged? Or
Yes. So in the end, they're then averaged. So, and that's just to produce this final face, which is the asymmetries removed.
Could you tell us a little bit what the goal of the project is?
Sure.
By averaging it out, aren't you losing information?
You are. You're losing information about the asymmetries. Okay, so what the anthropologists care about, right, is they want to, especially at this stage with the genetic information, what they'd really like to get to is try and understand sort of what genetic mutations are influencing the shape of the human face, right? So I won't get that far in this talk, but demographic variables we'll look at. So you want to understand what sorts of variables that you can sort of ask a person, how are they sort of going to influence sort of the shape of the face. And so I'll show you lots of examples of this. But how does, so if somebody gets older, right, or heavier or lighter, how does the shape of their face actually change? Yeah.
Did they think about why they need 7,000 landmarks? That seems quite a big number.
It may seem like a big number, but actually to capture the intricacies of, they want 7,000 because if they want to zoom in on the eye, so for example, I want to look at the shape of the eye, right? They want to have that sort of option, right? You don't want to go back later and have to sort of re-record. So I agree. If you look at sort of the face globally, 7,000 points might be a little bit much. But when you start moving into, zooming in on these different features, they're surprisingly complex. And so you're not going to have 7,000 points around the eye. So. Any other questions? Okay, excellent. Thank you. Okay, so as I was saying, so what are our sort of goals with this data? So we'd like to develop tools for associating faces and, in general, other manifolds. So I mean, as a statistician, I don't care that much that they're faces. It's more about the structure of the data. So what it is about the faces that I sort of need in order to develop tools for associating faces with covariates, okay, or potentially other manifolds of similar types. And then what we'd really like to do is, so I don't want to just sort of say that things are associated. I really want to understand how do these covariates influence the shape of the face, right? How does a particular genetic mutation influence the shape of the face? Does it do something with the nose? Does it do something with the eyes? And so with the anthropologists, they're not just going to stop there. They're going to look at particular mutations, and they're going to try to understand, okay, where did these mutations originate, right? And are these mutations, are they related to some sort of environmental factors? And so the reason that I got involved in this project is because I think that there's sort of a lot of smooth structure here that I think things like functional data analysis can exploit. And so when I sort of originally got involved in this project, it happened because I was teaching multivariate statistics at Penn State, and I kept having this one graduate student he wasn't even in my class, but he just kept come visiting me in my office, and he kept asking about this data. So how do I do this? How do I do that? And so after he asked me enough times, I thought, actually, this is a really interesting data set. And so that's sort of how it came about. But what they were doing just felt, I mean, it was reasonable. This is certainly not the problem, but it felt like there was sort of a lot left on the table that I thought we could do. Okay. And then ongoing work is we're doing variable selection with a larger number of genetic predictors. And this is happening sort of as we speak. Okay, so what is previous work on this? So this is a huge literature, especially if you're going to start talking about how to do sort of shape analysis. It's enormous. So I tried to list just a few examples of sort of more maybe statistically oriented, at least from my perspective, methods. But the key thing I think to keep in mind is that especially for a lot of practitioners, what they'll do is that they'll run through these sorts of classic shape analysis tools like Procruste's analysis to get everything nice and aligned. And then they'll take those 7,000 points and they'll just treat them as sort of a vector, right? And so what that means in this case, since every point is actually 3 coordinates, that means it's 3 times 7,000, right? So they have over 20,000 points, and they just treat it as just this nice long vector, and they do multivariate analysis with those. And so I felt like we should be able to do more, and certainly the shape analysis folks would sort of agree, because there's lots of sort of more sophisticated shape techniques which try and not just treat them as vectors. But maybe the one that's sort of most comparable to what we're doing is this paper right here by Porro Munez. So this is actually a functional data paper with faces. And the way that they analyze these faces is that they take a face, and they just lay it sort of flat. And then they view it as a surface, right? Which is sensible, I think. However, it's not really, I think, respecting the structure of what's going on with the face. Because this sort of laying it down is sort of completely arbitrary. And if anything sort of curves in at all, then it's not a function anymore. So this is not going to work. So you sort of have to lay them in a way and have to be really guaranteed that nothing is curving in on itself. But this is sort of most closely related to what we're going to do. So we're not going to lay them flat. We're going to do something a little bit different. Okay. And so manifolds in functional data analysis. So this has come up already in quite a few contexts. But mostly what's happening, and I think maybe Yang will sort of talk about this, Fang will talk about this a little bit more, is that you can have sort of these manifolds in FDA, but usually the way that they're viewed is that you have this 1 or 2 manifolds, and the data is sort of lying on that manifold or maybe just slightly off that manifold with some noise, which is certainly reasonable. Or things like Aston and Sangali, who sort of have a particular manifold domain, like the sort of the shape of a valve in the heart, and sort of then they measure a function on this domain. And that's not exactly what we have here. So basically the way that we're viewing this problem right now is that this is sort of, we're taking sort of the functional data perspective, which is to say that we're viewing each manifold as an object itself. And so in this sense, what we have is as many manifolds as we have units. Okay, and we want to analyze these things statistically. So I'll simplify this to a degree, but this is sort of the problem. Not that everything is just sitting on a single manifold or a couple manifolds. Okay, so this is not, probably don't really need to go over this much for this audience, but so what is a manifold? So just so we're on the same page. So basically a manifold is just sort of a structure. Usually you can think about it in RD, but it's basically a structure that when you sort of zoom in on it, it sort of looks like Euclidean space, but when you zoom out, the structure could be sort of much more intricate. And so, for example, if you have a line segment, this is a one-dimensional manifold. If you have a sphere, this is a two-dimensional manifold. And the faces are actually, you can view them as two-dimensional manifolds. So even though they might be sitting in 3D space, they're still sort of surfaces. Okay, so so they're actually not that complex as far as manifolds are concerned. And then the other important concept, I think, for manifolds is this idea of the atlas. So in terms of sort of, an atlas is sort of a way of traversing a manifold in some sense. So in order to construct an atlas, basically what we need to be able to do is you need to be able to take your manifold and you need to be able to sort of lay patches over the manifold. And sort of how many patches you need is sort of the chart. So how many charts do you need to cover this manifold? And so again, faces in this sense are actually a very nice manifold because you only really need one patch. Okay, it's not, you have to stretch it and you have to do these things, but you really only need one patch, so which means that sort of a face is a two-dimensional manifold, but the atlas, you can get away with an atlas with just one chart, which is quite nice. So that's different than the sphere, for example. Okay, and so this is just to sort of try and make this connection a little bit clearer. So manifold data analysis, since we have also, functional data analysis, object-oriented data analysis, any sort of data analysis. So we just try to make this clear that really what we're interested in is we're trying to analyze the manifolds as units. Okay, and the tools that we're using would basically put this under the branch of functional data analysis. But if you don't like that, you can sort of think about this also as sort of shape analysis or object-oriented data analysis or whatever one you prefer. Okay, so what are we going to do with this? So what's sort of the major perspective? So once you understand sort of what we're doing, I think everything follows pretty naturally. Okay, and so the way that we're going to sort of apply FDA techniques is that we're going to construct a domain. And this domain is in some sense going to be artificial. Right? So I have all these faces which are sitting in 3D space, but they're not really functions. They're just sort of point clouds. They're just sets. Okay, so in order to apply something like functional data analysis and try and take sort of advantage of smoothness, I need a function. I need a domain. Right? And so what we're going to do then is we're going to actually construct our domain from one of the faces. So you can do this with one of the faces in the data set. We ended up using sort of the average of the faces since they've been aligned. But it doesn't actually change very much. And so this is sort of not so surprising from a shape analysis perspective because sort of as Victor talked about, right, if you have these sorts of shapes, you can sort of align them. You can sort of pick one of them to do the alignment if you like. And so we're just taking this sort of a step further. So what we're going to do is we're going to take sort of each individual face. So this is Mark. This is Mark Schreiber, by the way. And this is just an average of the faces. Okay? And so for each of these, we have a correspondence between sort of each of the points here and the points here. Right? So we know which ones to connect. Okay? And so then we're going to view then each face as basically sort of a transformation of this common face, this sort of average face, which I think is sort of a reasonable way to think statistically, right? We think about things statistically as being there's some sort of average, right? And then I have some noise which sort of pushes me away from this average. And so in this sense, the noise is just going to be sort of this deformation of this average face into Mark's face, right? I have to take the cheeks and I have to do something like this and the nose and do something like this, right? And then I'll get Mark's face. And so then I'm going to do this with every face. So each face, so you can sort of stack them up. So each face is going to have this alignment to exactly the same average. Right? So exactly the same sort of common face. Yeah?
How did you say you dealt with the correspondence issue? You said it's just easy to correspond one point to another?
No, it's not easy.
Okay.
It's by design of this particular data set. So, and this is actually the point of sort of that careful pre-processing that they do. Because what they do is when they take that mask and they put them over the faces, you get the correspondence for free. Because that 7,000 points, they're all on that mask, and so they're all already aligned. Right. So if you have sort of much rawer data, this is the big issue, right?
What do you mean by average? A Frechet mean or
Of this guy? A literal average. So this is, we sort of played around with this to see how much it would make a difference. It doesn't make a huge difference. But this is literally, you take those 7,000 points, right? So that is to say, I take everybody's tip of the nose. I go across all my 6,000 people, and I just average the location of the tip of the nose. And I do that with every single point. So this gives me just sort of an average, a very average-looking face. And this is possible.
Then you must solve, in a sense, the registration problem before, right?
Yes.
That makes sense. I mean,
Yes. So, yeah, absolutely true. So the registration problem.
Take point-wise average. That would okay.
Yeah. So the registration problem has to be solved, right? And they have to be sort of not just registration. They have to be actually sort of really properly aligned. And so this is the whole point of that sort of pre-processing, is that the sort of the correspondence, this is taken care of by the mask. And then they do sort of classic shape analysis techniques to get all these faces sort of as aligned as possible. So you sort of, you shrink or move. But if you don't have that, then this average is actually might not even look like a face. Then it could look like anything. Any other questions? Right. Yeah, so in some sense we cheated because that's a real problem. And in other data sets it is a real problem. But in this data set it actually is not. It sort of is, we get it for free in some sense. I didn't pay the price though, Peter did. Okay. All right, any other questions on that guy? Okay, and so here's just some general assumptions. So I'll have a couple theorems towards the end, but this shouldn't really be taken in that context. I think this is mainly just about trying to outline what is the structure of the faces that in some sense we need in order for what I just did and what for all is sort of what I'm going to do, what would I sort of need out of these manifolds. And so some of these are just sort of what I've already said. So for each of my objects, so each of these samples, I have a random sample of manifolds. Each one should be compact and d-dimensional. In my case, they're subsets of R capital D. Okay, so they're sitting in a higher dimensional space, even though they have this lower dimensional structure. I have this sort of non-random manifold that I can do this alignment with, okay, so that I can actually build these sort of associations. And then I have an atlas, okay, so but in this case, I'm assuming that the atlas just has a single coordinate chart. So just like with the faces, I can cover it with a patch. That's not that crucial, actually, not mathematically. Computationally, it's very nice. But if you had, say, like, you needed sort of two charts or two patches to cover a sphere, that could be done. But it's just computation a little bit harder. Okay, and so really the last two things are really just where the functional data analysis comes in. So basically for each of these manifolds, I'm building a function, right? And so I'm building a function which takes sort of this sort of one manifold, this sort of nice manifold that everything's aligned to, right? And it associates to the function. So it maps to this individual faces, okay? And then to make everything much easier, I'm actually going to build these functions sort of off of a projected, flattened manifold. So in this case, since I can cover them with a single coordinate chart, it means that I can actually take this manifold that I'm aligning everything to, and I could just push it down to, in this case, for the faces it would be 2 dimensions. But basically I can push it down to R little d, right? And that just saves me a lot, actually. So it makes the problem just a lot easier. It's not, again, mathematically this is not the issue, but computationally it's very nice. Because if I need to compute distances along the manifold, this can be a little bit tricky, although there's definitely methods to do it. But if I push it down to R little d, I can now just use the Euclidean distance on that set. Okay, and so we'll see all of this in action. So now that I have these functions, I can do functional data analysis. And so to do functional data analysis, I need something like these functions are at least in L2. Later on, when you want to develop statistical properties, you need more than that, but this is at least a reasonable starting point. Yeah?
How is this pushing down this related to what you were talking about those other guys were doing, treating it as a surface?
So the difference is that they're viewing the function as basically this is sitting over the surface and the function is going like this. So what I'm doing is I'm actually viewing the function as from this face to this face, right? But when I open that up, I still have the correspondence to the right points. So the thing is, it's when I open that up, it's not that that's sitting on top there. It's still that I have this correspondence just right. So this is where I think one of the major differences is that it's not viewed as a surface. And again, it's not necessary. It's just that how much time do you want to take to build the computational tools off of a manifold?
So in other words, you're
Yeah.
saying you can retrieve the full R capital D information from the small R little d.
Yes.
It's bijective.
Yes. So you can go back and forth. This isn't a problem. Okay. But again, and that's because it's this sort of two-dimensional with this one coordinate chart, right? That I can actually do this. If I needed two charts like a sphere, I can't go down to R little d, right? I could go to probably a simpler shape, a simpler structure, but not that simple. Okay. All right. So sort of as I've been talking about, so the strategy now sort of computationally is that I'm going to use manifold learning to do this projection. So I have to take this template face and I have to push it down to R little d, but I need tools to do this. So there's a lot of tools. So manifold learning is a big area. And so I have quite a few tools that I can explore. So we'll explore a few of them and sort of see how do they do. Once I have them pushed down to R little d and I have my faces, I can now build up the functions. And so I'll build up the functions using a basis expansion, sort of classic functional data. And then once I have the sort of basis representation, then I can do really all of the functional data tools. I can do functional regression, the good kind, not the bad kind, and then other things like FPCA. I say good kind because it's function on scalar, which is easier than scalar function. Okay. All right, so in terms of doing the projections, or sort of using the manifold learning to project down to R little d, you sort of have a lot of tools. So this seems to be sort of a list of fairly common techniques. So principal component analysis, which is basically what this previous paper did to get them on the surface. So our sort of hypothesis is that PCA is not the right thing to do. And then some of these other ones, LLE, Laplacian eigenmaps, there's just lots of sort of examples. Our sort of working hypothesis when we were sort of doing this was that anything which sort of preserved local distances really well, we thought would do better in terms of sort of reconstructing faces, right? So if you think that these are sort of really smooth objects, right, then you might think that what you really need to do is you need to get those local distances right in order to get sort of the smoothness correct. Then I added in one spanifold. This one is probably most people don't know. I added it in because it did something very different. So the others look similar. They don't perform exactly similarly, but spanifold even looks very different. So I wanted to add this in. Okay, and so if you do this, this is what you get. So these are, this is the sort of template face up here on top. The green regions are sort of etched out here. I'll talk about the points. There are little points here. I'll talk about those in a second. But then these are all of the projections, right? So those principal components, LLE, Laplacian, LTSA. And so this is why I added spanifold. Because spanifold actually tried to unwrap the face. So it like tore it into pieces, which I found really interesting. And so actually we can sort of do a lot of this even with that as the sort of the domain for my functions. But it looks a little funky. There's like chunks of face missing. So there's like cheeks are missing or some tip of a nose or something. But in theory you can do a lot of it. Okay, and so in terms of building the basis, in terms of expanding the functions using a basis, we're going to use something similar to B-splines. And in order to do something like that, you really need a mesh. So you have to put down a mesh over your domain in order to get these basis functions. And so, as we sort of said, the things that you really worry about with these faces are what's going on with the eyes, the nose, right? Those are the harder structures. The cheek is an easy structure, right? You don't need very much to know what's going on with the cheek. So we have a much finer mesh actually around these regions than everywhere else. Okay, so So we're actually going to recreate, we're sort of going to build these functions with each of these domains. And we want to sort of try and assess how good are those reconstructions. And so we'll do this, I'll talk about this in a second, we'll do this using sort of a cross-validation approach. But let me talk about the basis functions we used. So we used Phelps splines by T. Ramsey, your son, not Jim. And actually, the reason that we wanted to use Phelps splines is because we wanted to give this one really a fair chance. So the nice thing about Phelps splines is they take into account this sort of domain in a better way. So the thing is, if you have to sort of move around objects and things, then it's sort of going to take that into account in a way that sort of using other methods might not. This is why we settled with Phelps splines. Now in the end, we used one of these other ones, in which case we actually started using some other kernel methods, and they work. I mean, they all work pretty similarly. You get a little bit, you can do a little bit better job with some of the kernel methods, but the ideas end up being the same. Okay, so we end up using Phelps splines, which you can think of them as sort of a generalization of B-splines, and you can sort of fit this basis expansion using sort of a penalized least squares approach on the Laplacian. All that software is available, and so it was actually pretty easy to implement. Okay, and so then these are sort of the results, and so this is a sort of a cross-validation. So we sort of rebuilt these functions for sort of a subsample, and we tried to compare the average of the rebuilt ones to sort of another group of average faces that haven't gone through this process at all. And so what we saw was that LTSA did the best. And this was closely followed by LLE. And so that actually sort of fits with our intuition, because those are the guys which, at least conceptually, seem to try and preserve local distances as sort of a priority, let's say. Okay, whereas PCA just finds a two-dimensional linear space, right? It's not trying to sort of get all of the local distances right. Okay, and so PCA does noticeably worse. Diffusion maps, which is sort of, it has sort of like a PCA involved, does almost the same. Laplacian does worse. Spanifold does by far the worst, which you would hope so if it's going to tear the face into little pieces. Okay, and so when you go through this whole process, so these are 3 examples of original faces, and these are reconstructed faces. So these are faces which have gone through this whole thing. They've been expanded using these basis functions, and then this is what they look like. So if you look really closely, I don't know if you can see from there, but if you look really closely, you'll see that even, the eyes still get smoothed over a little bit. Even with this really careful meshing, the eyes are still a little bit smoother than in the raw ones. Around the mouth, it's still a little bit smoother. We have actually now, by switching to kernel methods, we actually get those, we fix even those little things. But in terms of trying to find sort of major patterns and major features, we don't think it's too big of an issue, but it's fixed in subsequent stuff later anyway. Okay, all right, so once you have these functions, now everything should look fairly standard. So you want to do principal components, great. So principal components requires using a covariance function. However, the covariance function here is a little bit more complicated because you have any 2 points on your template face, and then for those 2 points you compute the covariance, but they're 3 dimensions, so that's a covariance matrix, okay? But that's still fine, it's not a problem. So, so you have your sort of matrix valued covariance function over this domain, and you just need to solve this integral equation to get the eigenfunctions, which is easy to do. Mathematically, to make sense of all this, you should at least have something like a second moment, but we'll worry about theory in a second. All right, and so if you do this with this data set, this is what you get. And the principal components actually, I think, look pretty nice. I sort of always worry about principal components that maybe you do reasonably well in the first couple, but then everything looks like junk later on. But they're not so bad. So what we've done here is we've plotted, because it's sort of hard to visualize these functions, actually. So what we've done here is we've taken this sort of template face, and we sort of look at where the principal component is pushing you. Okay, so red means it's sort of pushing you out. Blue means it's pushing you in. Right? So the first principal component, the sort of major mode of variation, is the face coming out, right? And the sort of center of the face and the nose coming in, right? Now that's unique only up to a sign, right? So you can flip it. You could think about the middle coming out and the middle and the sides coming in, okay? But the same idea still holds. And so in each of these you can sort of tell a similar story. So with the second one you sort of have the forehead, the nose coming out, sort of over the lip and the chin coming out, whereas the sides of the face are coming in, and so on. Okay, so each of the ones is not so hard to sort of imagine what's going on with these principal components. Okay. All right, and so so the thing with feldsplines, and this is why we really wanted to spend a little bit of time with the principal components, is the feldsplines actually did not really give us much in the way of dimension reduction. And even when we switched to kernel methods, we still couldn't get much in the way of dimension reduction using just sort of smoother. So you really, if you want to get some really good dimension reduction on this sort of data, it seems like you have to move to something which is data-driven. Otherwise, you're stuck in thousands of dimensions to get really good recreations. But with principal components, I mean, even down to 100 principal components, so 100 dimensions, you get these faces, I think, pretty nicely. So these are the same 3 faces. And you see going from 20 to 100 changes a little bit, but not too much. So in this case, feldsplines still need a couple thousand. Original data was 7,000. Now you're down to about 100, and you have the data pretty well represented. We'll do 200 for later analyses just to be safe, but this is sort of what we're going to work with. Okay. All right, and so I don't actually care about principal components. I only care about them as a dimension reduction tool for right now. Interpreting them is nice, but that's not what I care about. So what I'm going to do, though, what I really care about, though, is manifold regression, okay, or just regressing these objects that I've built onto other predictors, right? And that's what the anthropologists care about, and that's where a lot of statistics really starts. You have to be able to do regression. And so they can choose whatever predictors they like, things like height or weight or gender or whatever, and those are those x's, right? And so then I want to fit a regression model, right, where the y-ns, those are my faces, and now the beta j's, these are sort of more complicated objects now, but it's still not so bad. And so in order to fit this sort of regression model, I can do least squares, but I want to add some smoothness. It's not actually strictly necessary. You can do this without penalizing. But we wanted to smooth this a little bit to see if it helped. Okay, so again, we sort of do, we penalize each beta according to the Laplacian. And then our beta hat is just the minimizer of this guy. We use cross-validation to pick the lambdas. Okay. But one thing to keep in mind is that these betas, they're actually going to be linear combinations of principal components. And that really actually saves me a huge amount of computational time. So in order to sort of do this, especially in terms of selecting the lambdas, it can actually take quite a while if you don't reduce the dimension. And so by going down to 200, this becomes much more manageable. Whereas in higher orders, if you're still sitting in the thousands, actually this could take quite a while. Okay. All right, so here comes my only 2 theorems of the talk, although I'm probably in a location where theorems are probably good to talk about. But anyways, so the first one are confidence bubbles. So this is sort of so we'll have statistical tests that we'll use later on, which are just sort of standard statistical tests. But I sort of wanted to give, we sort of wanted to develop sort of a quick and dirty way of getting simultaneous confidence across the entire face. Okay, and so this is what we're calling confidence bubbles. So these are not based on simulation. You can compute these things exactly, but they are conservative. However, it doesn't matter how many points you observe across the face, they'll still control the type 1 error simultaneously across the entire face. And so the only thing that you really need is you just need that these beta hats, as long as they converge in distribution to a Gaussian process, and as long as you can get a hold of their covariance, then you can actually take this covariance and you can build these sort of bubbles, sort of pointwise bubbles, because we're not, everything is more complex now, and you can actually get simultaneous control of the type 1 error if you care about this. Okay, so we'll actually have statistical tests which are, they have exactly the right type 1 error. But if you don't want to go through simulation to try and get sort of confidence regions, then you can do this. It's fast. It's conservative, but it works okay. All right. Okay, and I thought probably this would be a decent audience to say, just talk about the optimality of this regression problem. So, so it turns out, so with Prof, Swipper, that's not even close to right, but I'm trying, who was actually a postdoc here a couple years ago, I guess. So we actually developed a minimax rate for this regression problem. And so the minimax rate sort of looks like the following. So basically you have n, which is the number of faces, or the number of units. You have m, which is sort of like the average number of points per face. And so then the regression, and so if you're using sort of, if the betas lie in an RKHS with a particular kernel, then the minimax rate looks like that. Okay, so in that's sort of maybe common in RKHS methods. And the h is, the little h is related to how quickly the eigenvalues decay. So if they decay quickly, then you get sort of a better rate. However, you can't get faster than parametric. So basically what you have is that if you have enough points, you will hit a parametric rate. And then you're not getting any better. It doesn't matter if you collect more points. And so actually, so this is sort of an interesting, anyway, so if you sort of move to a Sobolev space so you can interpret this h, then it turns out that h is actually p over d, where p is the number of derivatives, d is the dimension of the manifold, the manifold domain, not the outcome. The dimension of the outcome plays no role. It's only the dimension of the domain. Yeah?
Max here. I mean, max over which space? Over which
RKHS.
Huh?
Over the RKHS ball. So the beta R lying in an RKHS ball. So this is the space.
Which ball?
Reproducing kernel Hilbert space. So just imagine like a Sobolev space. So basically like a Sobolev ball. So with say p derivatives and the domain has d dimensions. Right. But you can go more general. So if you don't want to do a Sobolev space there, you can work with these RKHSs, which are a little bit more.
And you take a ball index.
Right. Yeah. Exactly right. Okay. But anyways, this is a little bit more interpretable now if you move to here, because then the rate now basically becomes 2p divided by 2p plus the dimension, right? So now you can really see the effect of the dimension of the domain. And this also tells you why you really want to appreciate this sort of manifold structure, right? By recognizing that that manifold is really just two-dimensional, right? You don't pay the price in the ambient space, right? You pay it in whatever the dimension of the manifold is. Okay?
This is an upper bound of the minimax rate, or is it the
That is the minimax rate. That's lower and upper. Okay. And actually, so if you sort of work this out, you can actually figure out where the phase transition happens. So basically, where do you transition from, when do you hit a parametric rate? And the reason this is sort of important in functional data analysis is that Jianling Wang has been proposing that basically where this phase transition occurs, that's the definition of dense versus, or that's the threshold for dense versus sparse functional data analysis, right? So basically, if you hit a parametric rate, that you should think of as sort of sparse. I should call it, not dense. They should call it ultra dense, but I'll just call it dense. So dense functional data analysis, whereas if you're in this regime, you're sort of in the sparse case. Okay, so this is telling you, that the smoothness helps in terms of hitting that parametric rate, but the dimension sort of hurts you. Okay, so you need sort of in higher dimensions, you need more points before you're going to hit that parametric rate, which probably makes sense. So, anyways, that's all my theory. Okay, so back to the problem. So these are just sort of all the variables that we included in this regression model. So this is taking all these phases and regressing simultaneously on all of these different predictors. So we looked at age, height, weight, genetic ancestry, and we threw in a couple interactions. We have so much data, you can throw in almost whatever you want. But we just sort of wanted to do all this just to see is it all working in some sort of cohesive way. And we even, in the end here, we even just threw in a noise variable just to make sure everything seemed calibrated. And so these are 3 different statistical tests. They're all using exactly the same estimates, but they assess significance slightly differently. So basically, you have principal components where you really reduce the dimension, and then you do like a chi-square type test. And then norm test, which just looks sort of like the L2 norm of the functions. And then what I'm calling choi, after one of my students, which is basically a compromise between the two. So you basically normalize by the eigenvalues, but not all the way to principal components. It's sort of in between. So it's a little bit more stable, but also you get some of the power in principal components when you have these effects in later principal components. So anyways, everything is basically significant. I mean, there's so much data, these are such big effects, it's just, there's no surprises there. Okay, and so you can also look at these guys, sort of visualize what's going on. So this is male versus female. So I think this is male is the baseline, and then you move to female. And so as you move to female, on average, the face sort of comes out a little bit. Again, the red's coming out, and the blue comes in a little, right? Just on average. Point-wise significance, you basically have everything is point-wise significant for for gender, except where it crosses. Where that's actually not significant. And then if you're worried about sort of controlling the type 1 error rate, you have overall significance just using these quick and dirty confidence bubbles. You basically get, everything is fairly significant except sort of more on the temples, sort of the tip of the chin, not quite as strong a signal. Okay. And then for ethnicity, so this is all, we're also treating this as sort of categorical. So if we compare, say, East Asian to Northern European, then as you sort of move from Northern European to East Asian, again, on average, sort of cheeks come out a little bit, nose, forehead, chin, they come in a little bit on average. If you sort of go to overall significance, then the effects are really strongest on the cheeks and the nose and the forehead, not quite as strong on the chin and around the temples. Anyway, so in order to visualize what's going on, so I'll give you one example and then another toy example in a second. So this is Mark. So to sort of really understand these effects, one thing you can do is you can take Mark and you can sort of start changing his variables, right? So you can make him female, which is actually a really big effect, but it's somewhat hard actually to see in the graphics, even though it actually is a really big change. You can make him younger. You can make him older, right? I mean, so older, it looks fairly reasonable, right? It looks like maybe he's aged. You can make him heavier. You can make him lighter. You can make them taller, you can make them shorter. You can really see how these different variables are actually changing the shape of the face. And, okay, so this is the most dangerous part of the talk because this is, who knows if this is actually going to work. So far, it's always worked. So this is a Shiny app. So far, it's always worked, but I haven't tried it out of the US during a presentation. So, okay, so this is on my website, though. Oh, actually, this worked pretty well. So this is on my website, so you can, if you want to play around with these things. So this is a very smooth version of Mark's face. Smooth only because the graphics actually take a while to render. Our statistical methods are immediate, but the graphical methods take a little bit. And you can actually play around then with Mark's face, and you can try and visualize what's going on with these different effects. So you can make him way, just for example, so you can make him way older. Let's see if I can do this without breaking everything. So make him older, sort of old, showed you older face. So you can make him older. You can make him shorter, example. I'm amazed that this thing is actually working. So short, sort of squishes in a little bit. And you can make him a lot heavier, which is, this is why you use a collaborator who's okay with these things. So he doesn't mind being distorted, right? So that's what Mark would look like if he was 90, way shorter and way heavier, right? Now, it's just a toy, but it's sort of, I think it's useful. These are such complex sort of models with such complex effects. Anything you can sort of help to really visualize the effect of these predictors, I think is pretty valuable. So, all right, so let's see what I have left. Control. All right, so with that, just some final concluding remarks. This is sort of a functional data approach to this problem. Lots of different ways you could probably approach this. Choose your favorite way. But I do think there's a lot of interesting opportunities in terms of bridging things like functional data analysis and shape analysis, and doing it in a way that sort of really uses both, right? I mean, I think this is what I really liked about Victor's talk, is that you really saw the interplay of both. And so for us, I think trying to understand some more about shape analysis in terms of the shape of the faces and how do we really, exploit that even further, I mean, it would be really, really nice. And so this is what I was really excited about coming to this conference, to hear about these sort of geometric features. And then sort of the other thing is sort of more practical, is that sort of what if the manifolds are more complex? So in this case, the faces are just fairly simple manifold as far as manifolds go. I can project them down without too much trouble. But you can imagine if I have something much more complicated, I might not be able to project it down, or if I even wanted to try and project it down, I might have to go to a simpler object, in which case maybe I would just give up on it entirely, then I would want to build everything off of the original manifold, which can be done, but it's computationally a little bit harder. You can't rely on quite as many sort of out-of-the-box tools, but certainly it would be interesting. So with that, thank you for your time.
Matthew, we already had a couple of questions.
Oh, yeah, that's good.
So are there more questions? Rainer?
Come back to this down projection from R capital D to R little d, right?
Right.
So, what did you compare? What happens if you ignore the manifold structure and you just this other dumb thing projecting down on R2 and trying?
Yeah, that's principal components basically.
Yeah.
So and it's about 5 times worse in terms of sort of cross validation error. So if you look at how bad the reconstructions are, in a cross validation sense of reconstructing a set and then not reconstructing a set and trying to look, you'd basically do about 5 times worse. So and it's there's just little things I think that it's just going to miss, and it's probably going to have trouble with the nose because you're sort of laying flat. The nose all of a sudden becomes this like, this huge change, and you might have trouble with the chins and things like this. So it does a bit worse. But I think the problem is not necessarily sort of completely ignoring the manifold so much as that it does nothing to preserve local distances, which if you're going to exploit things like smoothness, which is where I think FDA really does a good job, then you want to get those local distances right, I think. Mine.
But going back to the symmetry.
Sure. You guys waited a while. I'm impressed.
I was just, the pictures you had, I was expecting them all to look completely symmetric, all the colouring.
Right.
But they're not.
They're not.
Yeah.
They're not. This is.
The reason why.
They're not completely symmetric. I think at least a little bit has to come with sort of our treatment of the data. I think we have at least one step in there that's probably not completely respecting, it's not completely symmetric. However, it turned out that actually if you go into the data, the process of symmetrizing these faces actually turns out not to be exactly perfect. It's like very close, but there's like little differences. And so I think basically this is my interpretation, is basically what you're seeing is that there's sort of a cumulative effect, that nothing is quite perfect, and so then it sort of builds, and then at the end you get something which is like almost symmetric, but you notice some like little differences, especially like with point-wise significance where it's like, it could be very, very on the boundary. So then maybe on one side it's not quite there, and on the other side it is. So this is my.
Do you have access to both the original and the reflected one?
Yeah, we actually have, so I personally don't have it, but we can get actually the unreflected, unsymmetrized face or the reflected face. You can get sort of all of it if you like. Yeah.
Yeah, well, that's a pretty impressive talk.
Okay, thanks. I appreciate that.
And you lost me in several places.
Okay.
So, but one of the great pleasures in life is you lose control over what your children can do, and when you lose control over what the FDA does, you know you've made it.
Okay, good.
And as for Tim, he taught me everything I know. So.
Okay, good.
But nevertheless, going back to my days in psychology, which are still pretty important to me, there's been a lot of psychological studies of the geometrical properties of faces, and one of them that seems to emerge is that people don't like symmetric faces.
Okay.
They look artificial.
Too symmetric.
Your face is strongly asymmetric. Most people's faces are asymmetric.
Right.
And they have a sense that a symmetric face is hiding something.
I see.
Right?
Yeah.
And so I don't throw away those asymmetries.
No, yeah, I agree. We try not to throw away anything. Yeah. Oh, no, I agree. I think the asymmetry is an interesting question. I just sort of follow the lead of the anthropologists on this one in terms of what they like to do in their field. So. But you're right.
We still have some time. They just informed me that the coffee and tea is not ready yet.
Oh, I'm sorry.
Okay, well, then you're allowed to ask dumb questions, right?
Go for it. Anything and everything is okay.
Okay, well, what the hell is P and D anyway?
What are P and D?
Yeah, how big were they in your...
Oh, sure. So the capital D is 3.
Okay.
The little d is 2.
That's what I thought, but I was getting increasingly unsure.
No, it's okay. There's lots of notation flying around. Yeah, and I think I had a P. There was a P, I think, for smoothness.
Okay.
So
that's the number of derivatives.
Yeah.
How many derivatives then did you use?
I mean, so we just use 2. So I mean that on our penalization.
Yeah.
But in terms of those rates.
Well, if you use Fell-splines, they only have 1. But
I thought you can have higher orders than the Fell-splines.
you can in principle, but
I thought it was in the software. It could be one.
Software just uses Laplacian.
Right.
elements.
So yeah, it might just be one. But this is
you can extract two by comparing adjacent triangles, of course. I mean, that's another.
'cause we played with this for a while to build these.
What Eilers and
Yeah.
did in L1. Yeah, this was sort of very curious about that. And
But that's mainly about the rates anyway.
Yeah.
So and which is something, of course.
now, now again, you know, coming back to the dynamics of all of this, of course, you know, there's flow going on here, spatial flow, and so it certainly seems likely that if you're going to reduce thinking about reducing dimensionality, estimating that flow would be an interesting way to go towards a lower dimensional representation.
So in sense of flow, you mean flow from the template to the
Yeah, sort of
Yeah.
the flow and the registration that's done continuously.
right? I think you're right. Well, and I think that a lot of the spatial folk.
Certainly, the information in things like age and weight is clearly in the flow.
Sure.
You know, as you age, you lose the tissue, you lose moisture in your
Right.
tissue, the tissue sags, and so on. So, I think looking at the flow, looking at the dynamics, might give you a lot more impression in the complexity of what's going on.
Yeah.
But I mean, could I do that before noon? Unlikely.
Okay. We'll have to look into it.
I have a question. Do you really need to parameterize your template on a plane?
No. Now, I mean, mathematically, definitely no. But in terms of computation, it just makes it simpler. So it means.
Well, exactly. It makes it simple.
So the thing is, so if you're talking about building off of a plane, then there's a huge amount of computational tools that are available to you, right? Building basically with a plane and building basis functions off this plane, it's much easier. And in terms of calculating distances, right, it's Euclidean distance. If I want to build off the face, it can definitely be done. And I think folks like Laura, they work directly on the manifold. So, and that works. It adds a layer of complexity that we sort of we were really interested to see if we could remove it, right, and still do a pretty reasonable job. But you don't have to do it.
Yeah, my question was because at the end of the day you use falsify, which is easily extendable to the case of the manifold. So
At the end of the day, this is all with Feldspline. We've switched over to kernel methods. The kernel methods, you can do the kernel methods as long as you can compute the distance along the manifold, and then that'll all go through.
Well, one thing we've done is to switch to Bernstein polynomials, which
Okay.
are really a much more powerful basis system.
I see.
I'd recommend thinking about those.
Okay, we'll take a look. Yeah.
Okay, then let's thank both speakers again.